We've been lucky enough to catch him with the assistance of the Society for Popular Astronomy, who he's been signing books for all afternoon. He probably has severe writer's cramp by now. He's Professor of Particle Physics at the University of Manchester, and he's involved in the experiments at the Large Hadron Collider at CERN in Geneva, where a microscopic version of the Big Bang was recreated in November last year. And he's here to explain how experiments like the Large Hadron Collider help us to understand the incredibly hot and dense conditions in the early universe, and what that tells us about the origins of stars, galaxies, and life itself. And you'll know him from TV programs such as Wonders of the Solar System and the recent Stargazing Live. And here he is, live on the West End stage, Brian Cox.
Ian said that he'd already advanced my first slide to the second one, so he's already pushing me to get a move on. Because I thought it just started. Yeah, as Ian said, I'm not going to talk much about astronomy today. What I want to talk about is the Large Hadron Collider. But then I hope to draw out some of the... Actually, one result we've already got that has a direct relevance, potentially, to understanding, in fact, the cause of neutron stars, the neutron stars behave. But also then at the end, to speculate on things such as dark matter, and one of the biggest questions in physics at the moment, which is the strength of gravity and why it's so weak. Well, let me just introduce this machine to you first. If any of you don't know what this thing is, it's the Large Hadron Collider at CERN in Geneva. It's 27 kilometres in circumference. We always put them near runways, these things. So that's the airport, the Geneva Airport runway, just to get some sense of the scale. The biggest scientific experiment ever attempted. The job of this thing is to accelerate protons, so the nuclei of hydrogen, to 99.999999% the speed of light, and send one beam of those protons around one way, one beam around the other way, and then collide them together. And if any of you are fans of Einstein, it's interesting to note that if you go that fast, then this whole machine looks to be about 4 meters long to the protons because of something called Lorentz Contraction. Or another way of saying that they're going very fast is that time passes 7,000 times more slowly with those protons than it does with the scientists sat on the surface watching them. So it's a very ultra-relativistic machine, if you want to put it like that. This is a shot of the inside of the machine before it was completed. It's nice because you can see the LHC itself, which is this thing here. It's a pipe which is, I'm told, exactly 1 yard across, which annoys the French. The reason is that if you want to build things with a lot of pipes, then using the pipes that the oil industry use are cheaper and easier to do, and apparently that's the standard oil pipe, 1 yard across. So there it is. But these are the beam pipes themselves, so these are the tubes that the protons circulate around the ring in. So they're not very large at all, a very high vacuum. And the beams in there, the beams of protons, there are billions and billions and billions of protons in each beam. When they cross, when they collide, they're about the diameter of a human hair, but they carry the energy of an aircraft carrier travelling at 35 miles an hour. So they're incredibly high-intensity beams of protons, which is, of course, how we can recreate the conditions that were present less than a billionth of a second after the universe began, which is the aim of this machine. And for the engineers amongst you, I think it's just interesting to celebrate the engineering. These things here are what's called superconducting cables. So they're cables that if you cool them to about 1.9 degrees of absolute zero, so about minus 271 degrees C, then they have no electrical resistance at all. They're actually a niobium titanium alloy. And these tiny bits of fuse wire carry a current of 9,000 amps when the machine is operating at full power. You may remember we had a slight accident when we blew the machine up. And that was actually due to a helium leak, which allowed these wires to stop, to rise in temperature a bit and stop being superconducting. And you can imagine, if any of you know anything about electricity, that if you have thousands of amps inside things that big, you get a bit of a pop. So, anyway. So I mentioned that we collide the beams together. We can collide protons together up to 600 million times every second in the machine when it's running at full power, for luminosity as it's known. And each collision happens inside 4 detectors, 4 digital cameras essentially. And this is the one that I work on. It's called the Atlas detector. It's big, as you can see at the top there, 44 metres wide, 22 metres in diameter. It's 7,000 tonnes of digital camera. We have the standard EU-sized person there, so you can get some sense of the scale of it. It's an enormous machine in itself. It's got more components in it than a Saturn V rocket. And when you think that most of the components of Saturn V are things like rivets and structural things, this thing is a very, very, very complex machine. The protons collide together in there, so 2 of them just bump together, and you get hundreds of new particles showering out in that collision. And the idea, what this thing does, is to patch them all together, so detect as many as it can do. You try and recreate exactly what happened, and you can build a picture of that collision, essentially a picture of the early universe. So I think one good way of thinking about this is it's like taking a camera this sophisticated back to a billionth of a second after the universe began and taking many, many millions of pictures per second. This is a very famous picture of the Atlas detector during construction, which is nice, I think, because you can see the inside of the detector. Actually, if I go back one, these things are magnets here. So they're magnets because if you produced electrically charged particles in the collisions, then the magnetic field bends them and that allows you to measure their momentum. Essentially, the product of their mass times their velocity is one way of identifying them. So these things here are those things there, just to get some sense of scale, and there's a real Frenchman stood in the middle. This is where the collisions happen. This is another picture of the so-called inner detector going in there. Again, just to get some sense of scale. This is just the inner part of the Atlas detector being wheeled in during construction. And this is a picture of one of the collisions. It's a computer display of one of the first collisions, actually, in Atlas. So the collision point is there. This is a kind of a schematic view of that huge barrel, and you see all the new particles going out, some of them curving, which are electrically charged. So I'll show you some more pictures, actually, of collisions later, and a couple in particular that are of interest that we collected in the last few months. So don't get too confused. I don't want to scare you with equations or anything, but I just want to explain for a couple of minutes what particle physics actually is, because I think there's 2 really basic ways of looking at it. And this is one of the ways. This is an atom, the structure of an atom. There's the nucleus, and here are the electrons. Quantum mechanics tells us, or nature tells us, quantum mechanics is the theory that describes how this works, that electrons can only go in certain places around an atom. And they jump up and they jump down. And when they jump up and down, they emit light. And this is the key point. So we know that the energy of light emitted, so that means that the jump, essentially, that these electrons can make inside atoms, is related to the frequency, which is related to the wavelength. And one way of looking at particle physics is that you can't see things that are smaller than the wavelength of light you use to look at them. So in order to get to see very, very small things, you need very high energy light. You need energy to be big. And so one way of looking at particle accelerators is they provide the energy to provide very small wavelength light to see very small things. It's also worth mentioning, actually, that this quantum mechanical structure of atoms, the fact that electrons jump up and down between orbits, is the reason that we can measure the redshift of stars and galaxies, because each particular element has different positions of the electrons around it, and that means that they absorb light and emit light in particular ways. You see the fingerprints, and this is the spectrum of the sun, actually. So you see the fingerprints, for example, of sodium, sat there in the yellow light of the sun, and you can measure how fast things are receding away. Well, that's an aside. What I wanted to say was that this is the way that traditionally, over 100 years ago and onwards throughout the 20th century, we looked at the structure of atoms. This is quite a nice one that's from over 100 years ago now, and it's a graph, a plot of the scattering of electrons off helium atoms. So basically what was done, this takes about 1902, was that a beam of very low energy electron was bounced off helium atoms. And all I want to say about this is you see peaks in the scattering. So what you're seeing here actually is the energy of electrons bouncing off helium atoms. And peaks mean structure. In the case of helium actually, these 2 peaks here correspond to the fact that there are 2 electrons in helium that can be knocked out of the helium. So one way of measuring the structure of matter is to shine light in it with ever-increasing energies. If you wind forward to the 1950s, this is exactly what was done with the atomic nucleus. And whereas these electrons, this funny unit of energy we use is called an electron volt. I'll give you the precise definition. It's the amount of energy an electron gets if you accelerate it through a potential difference of 1 volt. So a 9-volt battery will give you a 9-electron volt beam of electrons. These, to get helium, to see the structure of helium atoms, you need about 200 electron volts, 200-volt battery, essentially. These, in the 1950s, are electron beams scattering off nuclei with energies of 150 million electron volts. So in the 1950s, you've got to 150 million volt batteries, essentially, and you bounce off nuclei and you see peaks. And of course, that means the nucleus is the point, it's full of protons and neutrons. Wind forward to the place I did my PhD in Hamburg. This is called the HERA particle accelerator, and it's about 6 kilometers in circumference, so not as big as the LHC. It sends electrons around one way, and protons around the other way, and the job of this thing is to shine light from the electrons, essentially, onto protons to see what's inside protons. That was done. This is one of those pictures, again, very similar to one I showed you from the LHC. It's a picture of an electron coming in, hitting the proton beam, bouncing off backwards like that, and knocking something out of the proton. And from these experiments, all the way through the 1990s and into the 2000s, we mapped the structure of the proton in readiness for LHC. Because at LHC we collide protons together, and if you're going to see new things in those collisions, you need to know exactly what the proton's made of. And I thought I'd just show you one graph for the aficionados of the current state of affairs, really, the state of the art and the structure of the proton. And you present it as fractions of the proton that are made of different things. As I'm going to say in a minute, the proton's made of quarks, the lower sublevel below protons and neutrons. It's actually made of 2 up quarks and 1 down quark. And you can see that in this plot, actually, because there are the up quarks, and they carry about 2/3 of the momentum of the proton. And here are the down quarks, and they carry about 1/3 of the momentum of the proton. So if you want to know the evidence for quarks, then it's here. There are the up quarks, there are the down quarks. Interestingly, you may have known that protons are made of quarks, but these are strange quarks that sit inside the proton as well, a different kind of quark. And these are things called gluons, which also sit inside the proton. I'll mention those now. What are those things? Because you might ask, well, on the eve of the LHC, so now, the LHC is running, what do we know now before we make new discoveries at LHC? This is what we know now. So this is the complete set of particles of matter and 3 of the 4 forces of nature that stick the universe together. So this is everything you need to build a universe. In fact, these 4 are everything you need to build a universe. So I just mentioned the up and down quarks. They make protons and neutrons. 2 ups and a down in a proton, 2 downs and an up in a neutron, essentially. This is the electron, which goes around the nucleus to make atoms. And this thing is called the electron neutrino. The electron neutrino is perhaps an esoteric particle. Perhaps many of you have never heard of neutrinos, but they come streaming out of the sun in their billions every second. Because what the sun does, essentially, is convert hydrogen into helium. And every time it takes 4 protons, so 4 nuclei of hydrogen, and converts them into 1 helium, it has to release neutrinos. A couple of neutrinos actually come out. That means that there is something like 60 billion neutrinos per centimetre squared per second passing through the Earth. So if you hold your thumb up now, there are 60 billion of those things every second going through your thumbnail. You don't feel them because they only experience something called the weak nuclear force, one of the most short-range forces of nature. So those neutrinos would have to pass very, very, very close to an atomic nucleus in your finger or in your head or indeed in the Earth to bump into it. So they stream through the Earth relatively unimpeded. So that is everything you need to make a universe, as far as we know. Because you can make protons and neutrons and atoms, the sun will shine and the neutrinos will come out. That's fine. For some reason, and we do not understand why, we have no idea, nature chose to make 2 carbon copies, essentially, of those particles. So this thing here is called a muon, and it's exactly the same as an electron in every way. It's identical. Same electric charge, same properties in every way, except it's heavier. And then there's another one called the tau, exactly the same. And they sit in families. So the up quark has the charm at the top, and the down quark has the strange, which I said there's some of those inside the protons, and bottom. And these things are identical in every way, except they're heavier. Same for the neutrinos. We have no idea why that pattern exists. But when you look at it, if you remember your chemistry back in the 19th century, it looks like a periodic table. And Mendeleev's periodic table told us that there was structure in atoms. And indeed, it was the key to understanding the structure of atoms, the structure of elements. In the same way, there will be a reason for that. I mean, it's too regular to be chance. But if you ask a physicist now, why do these two exist? They would tell you, we don't know. They don't seem to be necessary to build a universe, but they're there. We also know that there are very unlikely to be any more. So, in terms of these generations of matter. So, a mystery. What you also see on here are these things, the blue things, which are the force-carrying particles. So this thing is the photon, which in a particle physicist language is the carrier of electromagnetism. So if you ask a particle physicist why does an electron go around the atomic nucleus, they would say because a photon jumps between the electron and the nucleus, and that carries the electromagnetic force. In the same way, these two things, which we're going to meet in a minute, carry a thing called the weak nuclear force. I mentioned that. That's the thing that allows the sun to shine. It's the thing that can turn a proton into a neutron. The W and Z particles carry that force. And this thing I also mentioned, the gluon, is the thing that carries the strong nuclear force. That's three of the four forces of nature. Electromagnetism, weak nuclear force, strong nuclear force. There's also gravity, and I'm going to mention gravity at the end of the talk. It is far too weak to have any bearing on experiments at the LHC, as far as we know. But I want to caveat that, because there's some interesting caveats that I want to get to at the end. So that's really a picture of what everything in the universe is made of, apart from things like dark matter, which I also want to mention at the end. And three of the four forces of nature that stick them together. This is a nice picture, actually. I just wanted to show you because the Z particle might be unfamiliar, but we're making them all the time now at the LHC. One of the first things you do when you turn a new machine on is look for exotic things that you've already discovered somewhere else. These things were discovered in the 1980s at CERN. And this is a Z particle contains 2 electrons. So that's the Atlas detector again. And this is kind of unfolded out to show you the energy that's carried by things. And you see that all the energy in this collision is carried by 2 electrons flying out. That's a Z particle being made. And this one is actually a more complex event, but I think it's quite interesting. What it is a W and a Z particle being made at once in one proton collision. The Z particle is decayed to 2 muons this time, went flying out. So that's the Z decaying. The W goes to an electron and the neutrino. And the neutrino, as I mentioned, you don't see. And so it's labelled here as missing T, missing energy, basically. So one of the challenges in particle physics, actually, is to find the things that aren't there, which you need to do in order to reconstruct the fact you've got one of these W's there. But there it is, and it's very easy to do, actually. So there's the W and Z thing. This one, I just want to, this is the last collision I want to show you. This is a very recent one, and it actually made the press. It was so interesting. We can also run LHC in what we call lead-lead mode. So we don't have to collide protons in LHC. We can collide the nuclei of lead or the nuclei of gold in the machine. It's designed to do that. When you do it, you make something called a Quark-Gluon Plasma, which is what we think the universe was like about 1 millionth of a second after it began. So a soup of quarks and gluons before the universe was cold enough for those quarks and gluons to coalesce into protons and neutrons, and then onwards into hydrogen and helium, the building blocks of stars. So this is a picture of 2 lead nuclei colliding. And it's interesting because when things collide together, then usually what happens is something goes flying out that way, and in order to balance it, something has to go flying out that way. It's just a conservation of momentum, we've got a technical term for it. But what you see here is that something went flying out one way, and nothing came out the other way. And what we think happened is that this collision happened very peripherally, so the lead nuclei just glanced off each other. You've got this big ball, which was essentially a quark-gluon plasma, like the early universe. And then right at the edge, this collision happened. So a quark or something went flying out that way. But the one that went flying up collided so much with the quark-gluon plasma that it just lost all its energy and didn't get out. Now, that was a surprise, because the models of quark-gluon plasmas didn't suggest that, which sounds quite technical, but actually, quark-gluon plasmas are what we think are present inside neutron stars, hearts of neutron stars. So, to model the interior of things like neutron stars, you need to understand this state of matter, the quark-gluon plasma. And this was a result, a surprising result, which is actually still being interpreted. So we've got hundreds, thousands of these collisions. For the first time, we've seen this rather odd behaviour in quark-gluon plasmas. So that's what probably the most interesting new result that's come out of the LHC to date. Now, let me just tell you now, because I want to move on to speculation, to what we hope to discover. So that's the results we've discovered to date. One thing, of course, we do is we look for substructure again inside the quarks, because we've gone up with a tremendous leap in energy. So remember, the wavelengths of our light have gone down and down and down. So we look for the peaks in the scattering graph. You always do that when you go up to a new energy frontier. This is a search for that peak. So the blob, the red blob, sorry, the black blobs there, the data, scattering data. And these are actually simulations of different models of substructure inside quarks. So we want to look for new particles that build up the quarks. And you see there's no hint of them in the data, otherwise you would have read about it, because we've found a new layer of matter, essentially. But these are getting more precise all the time. So with every day that LHC runs, we're pushing these curves down and ruling out different models of what might lie beneath the structure of quarks. So that's one thing we're looking for. The other thing, though, is this thing called the Higgs particle. And I'd like to spend just a couple of minutes saying what that is, why we think something like it exists, and why we're so intent on finding it. So this thing I showed earlier, the known particles, we have a theory for that. I mean, actually, Ernest Rutherford said, all science is either physics or stamp collecting. What he meant by that is that you don't just collect the stamps, which is what we've done there, essentially. We've discovered all these new particles. You need a theory, you need a mathematical model to be able to understand what's happening and predict new things. We have it, it's very simple. That might not be your definition. It's called the standard model of particle physics. But it is simple if you think about it, because it'll fit on the front of a t-shirt. But it describes everything in the universe that we know of, other than dark matter and gravity. So 3 of the 4 forces of nature are in there. So electromagnetism, the nuclear forces that stick the nucleus together. All the particles of nature that we know of are in there. And so, in fact, it's a tremendous achievement, because in principle, every phenomena that we know of, other than gravity and the nature of dark matter, if you want to put that in the phenomena that we know about, is in that equation. And I want to just spend about a minute. Actually, Ian, how long have I got left? 12 minutes. I will spend a minute then, doing a complicated bit. I want to uncomplicate it for a minute. This is just for the connoisseurs, but I think you might like it. I've got enough time to talk about it. So this is that equation. If you take all the forces of nature out, and you take this Higgs thing out, which I'm going to talk about in a minute. So all it is these things here are the matter particles. So they're actually called quantum fields. So one way of thinking about electrons is that they're not just point-like particles. In fact, they're not just little points. They're actually extended objects. And you can imagine it like a field, the electrons. So with hills and valleys, if you put one in this room, it would spread out this field to fill this room. All the particles of matter, all those 12 particles are sat there inside this little thing here. Now what was noticed way back, so 70 years ago or so, was that these fields, these descriptions of the particles, have some freedom in them that is not observable. It seems like some extra freedom that you don't need. And it's called a gauge freedom. It's called a phase, essentially. It doesn't matter what it is. One way to picture it is that they're like little clock faces. So you have a mathematical description of an electron, and it has a little thing like a little clock hand that you can move around, and it shouldn't make any difference to anything. It seems to be redundant. It's an extra bit of mathematics that you don't need. But what was known was that although you could move all these little clock faces together, so you could wind them all around in parallel, and nothing happened. In the description of physics that they had 70 years ago, if you moved them around individually, so you're allowed to, like this, just turn them all to different angles, then although they shouldn't matter, they did. And they messed up the description of the universe in this equation. So the question was asked, because physicists like to play around, what would you have to do to this equation to fix it up so it doesn't matter where we turn all these little clock faces? And the answer is exactly that. Right? Well, that's interesting, because what I've done there is I've put the forces of nature in. I've put three forces of nature in: the electromagnetism, the weak nuclear force, and the strong nuclear force, and I've defined exactly how they work. And it's done in the standard model by just thinking about these little clock faces. So the forces of nature in this language are a consequence of demanding that the equation doesn't care where you turn on the little clock faces. That's called gauge invariance, and it's a very, very, very powerful principle. I'm sure you might agree it's aesthetically pleasing. It's very tempting to say, well, there must be something in that, because you can invent the forces of nature by just demanding that these little clock faces can be moved all over the place. It's a fascinating property of the standard model. The problem is, it doesn't work. Right? Exactly. And the reason it doesn't work is because particles have mass. So if every particle in the universe were massless, then that principle would hold, and it would be beautiful, and everything would work, and we'd be marvelling at the aesthetic beauty of it all. It doesn't work because there are masses. So physicists being physicists, they then asked the question in the 1960s, how could you fix it up so you can have your cake and eat it? I want that, I want gauge invariance, it's beautiful, but I want masses as well. And you can do it. And you do it with those two lines. Those are called the Higgs mechanism. And this thing here, this symbol, is the Higgs field, the Higgs particle. Right? So what the Higgs particle does is it gives masses to the particles in the standard model whilst preserving the mathematical beauty of the standard model. This is interesting because it's all aesthetically motivated in a sense, but now there's a lot of experimental evidence that this is nearly right, except that we haven't found that yet. So the LHC is focused on looking for that thing. And what is true to say is if that thing exists, if the Higgs mechanism works and exists, the LHC will find it, because there's a maximum mass that particle can have, a maximum amount of energy you need to find it, essentially, and we've got far more energy than we need at LHC. So if that's true, we will find that. There's a great analogy how it works, and I think I just want to share it with you. It's a very famous analogy, because you might say, well, how does this Higgs do its job? What it does is the Higgs field permeates the universe. So literally everywhere is full of this thing called the Higgs field. It's almost like a cosmic treacle that just fills the entire universe, a background field everywhere, represented by these party members at a Conservative Party conference. And you'll see why I say that in a moment. The story goes that back in the 1980s, Margaret Thatcher was thinking about whether we needed to stay in CERN, and a competition was run for scientists to send in on one sheet of A4 in language even a politician would understand what this Higgs particle is. And the story goes that if the science minister understood that, then CERN would be funded and we would be able to go and search for it. And this is the analogy that won. So the Conservative Party members. These represent the Higgs field. Then, if you imagine that someone walks into the room who isn't very popular, so someone who nobody knows, and they start walking through the room, nobody talks to them, they don't interact with these people, they don't interact with the Higgs field, and so they can move through the room unimpeded. So that essentially is a particle like a photon. It's something that moves through the universe at the speed of light. It's massless. So it's massless because it doesn't interact with the Higgs field, because it doesn't talk to any of the Conservative Party members, essentially. And imagine someone very popular, very important, walks into the room. And then everybody crowds around them because they want to talk to them. All these little Higgs particles interact with that person, that particle, and they're slowed down. So their passage through the room is slowed down. They acquire mass by that mechanism. That's exactly how the Higgs mechanism works. So, in a way, you might be able to see how you can protect all this beautiful mathematical elegance and simplicity, because what really happens is the mass is almost not there. It's not quite mass. It comes via an interaction with something else, by an interaction with the Higgs field. So that's how the Higgs field allows you to keep the beauty of the standard model and get masses for the particles. So, as I say, we just have to find them. This is a simulated collision in which a simulated Higgs particle will occur. So we know its properties, what they must be, if this story is true, and we're searching for it now. And if the LHC continues to run as it is now, which is beautifully, then we might begin to see hints of these things soon. I mean, we haven't done, I don't have any inside knowledge about that, we haven't seen any hints so far, but we're beginning to get to the point where we have enough data that we might begin to expect to see hints. So, in the last sort of minute or so that I've probably got, I want to go back to that idea of gravity, and I want to look at the other way we can look at particle physics. Because the other way is that the universe here, the complexity that we see in the universe, is really a property of an old and cold universe. So stars and planets and galaxies and people, civilizations, are really things that crystallized out of the universe as it cooled and got older and older and older. As you go back in time, then one way to think about it is that the universe gets hotter and simpler. And as I've shown, at the energies that you get in particle accelerators, which are something like 1 billionth of a second after the Big Bang, the universe is astonishingly simple. It's made of just, as far as we can tell, 12 matter particles. So that journey back there in time is what the LHC does. Well, there are 3 fundamental numbers in the universe that we can use to address this problem of how far do you have to go back to see it become so simple that gravity joins the party, right? Because gravity is so weak that we don't see it at these kind of energies that we see today. How far in time do you have to go back to see that? Well, you can estimate that by taking the things we know about the speed of light, Newton's gravitational constant, Planck's constant, some of the fundamental constants of nature, and you can arrange them to find a length, a mass, and a temperature. And because that's kind of quantum mechanics, essentially. This is the thing that describes gravity, the speed of light. If you arrange them in such a way that you find the temperature, then that temperature is essentially the temperature which you would expect gravity to start being important. And it turns out that it's enormous, right? It's 10 to the 32 degrees. Kelvin, Celsius, no matter what, 10 to the 32, 10 to the 32. Right. Another way of saying that is that the natural mass for particles in the universe that you would expect is something like, what, 0.00001 of a gram, 10 to the minus 5 grams. That's heavy. Right? That's not an electron or a proton. That is extremely heavy. That's a piece of dust. Right? So one of the big paradoxes in physics is that all the structure you see in the universe, the particles and the forces, seem to live on one side of an equation. But because gravity is so weak, it seems that they're all kind of wrong in some way. They're all far too small and far too light. Why is that? This is a huge question. Well, another way of phrasing it, as I mentioned before, is to say that 3 of the 4 forces of nature are all pretty much as strong as each other, give or take. There's a strong force, electromagnetism, and the weak force. They're within a factor of 100,000 of each other, which is not much, given that gravity is something like 10 to the 40 times weaker. It's a million at least times weaker than the others. This is a huge question. Now I'm going to skip. Actually, no, I don't want to skip this. Let me tell you about this, because I'm going a little bit over, but there we go. Sorry, Ian. Let me tell you one of the other problems that occurs because of this. One of the problems is that when you look at the Higgs particle, then you can calculate its mass, or what it should be, or how it should change at least in the standard model. And what happens is you get immense problems. It's called fine-tuning, and it's related to this problem of gravity being so weak. I mean, essentially what Higgses can do is they can fluctuate into other particles. So they can go along, fluctuate into these 2 top quarks, fluctuate into them, go back to a Higgs again. And what you find is that you've got to consider all these little fluctuations all the way up to the so-called Planck scale in energy. So you've got to consider what's happening all the way back to temperatures very close to the beginning of the universe. And this makes a real mess of the standard model, because it really tells you, as I mentioned earlier, that the Higgs particle shouldn't be in the mass range we need it, this kind of 120 times the mass of the proton or something. It should be enormous. It should be like 10 to the minus 5 grams or something. It should be as heavy as a piece of dust, which ruins the whole thing and makes a complete mess, I should say. How do you get around that? Well, there is a theory that gets around it, and it's called supersymmetry. Now, supersymmetry is incredibly interesting for particle physicists because it gets around a lot of these technical problems. It does it by introducing a mirror set of particles into nature. So essentially, you double the number of particles. That looks like it's not a simplification. But some very beautiful things happen. One is that all these little problematic loops that cause all the masses to go all over the place all cancel out beautifully. The other thing is that forces of nature seem to unify together. That's interesting. So this is a picture of the strengths of 3 of the 4 forces of nature. The weak force, electromagnetism, and the strong force. What you find in the standard model is that when you calculate how those forces change as you go back in time to the start of the universe, they almost seem to meet at one point. But actually they just miss. So it almost looks like the universe is getting so simple that 3 of the 4 forces of nature are the same thing, but they just miss. What happens in supersymmetry is you do the calculation, and this wasn't put into the model, and those forces all meet. So it looks like this is kind of circumstantial evidence that something like this is an interesting thing to do. The reason I say that at Astrofest is because the other prediction for these things is that the lightest one is very heavy. It only interacts very weakly with other matter, and it should have been produced in copious numbers in the early universe. In other words, the lightest of these supersymmetric particles is the prime candidate for dark matter. So the other thing to say, that's fascinating in itself, is if all this is true and all these beautiful calculations work, and the thing I skipped through quite quickly about the Higgs mass is to be fixed and solved by this theory, then these should be within the reach of the LHC. In fact, they need to be within the reach of the LHC. So many physicists, if you ask them, would claim that the first discovery of LHC is likely to be the supersymmetric particles, and therefore probably the nature of dark matter. And that could happen within the next year or 2, because if these things are around, they're rather easy to see. Now, in the last 1 minute, because Ian stood there and he said only 2 minutes, let me just say one more thing about gravity. The other big question, this big problem, is why gravity is so weak. It caused all these problems in the first place, essentially, and you can dodge it to some extent with supersymmetry. This is where you get all the black hole stuff from. Right? So you can ask the question, why is gravity so weak? One answer is that there are extra dimensions in the universe, which sounds a bit odd. You think of the 3 dimensions of space in this room and 1 dimension of time. So imagine we're on a 4-dimensional sheet, and that is the universe. Another way to look at it is that that could be a sheet, a 4-dimensional sheet in a much bigger dimensional universe. And you can start to calculate the properties of this. Why does that help? Well, the picture is that gravity lives on one sheet. The picture is that everything we know of lives on a sheet. So imagine it's just 2-dimensional for the sake of picturing it. So here's our sheet that we all live on. The strong force, electromagnetism, the weak force, light, everything that sticks everything together, all the matter particles are confined to this sheet, floating around in a big universe like this room. Gravity in these models, these theories, can come off the sheet. And so what you're saying is, in essence, gravity is as strong as everything else, but because it's the only force that has to bother with all this, the rest of the universe, then it gets watered down. That doesn't sound like an explanation, but there are experimental signatures of that. One of them is the production of things called mini black holes. Right? Now, the mini black holes, if you can produce them, evaporate away very fast, and blah, 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 all that sort of stuff. But I thought it was just interesting to end the talk to look at a few of the comments that were made about these things, because of course they scare people. That one was my favourite headline from Gizmodo. It's kind of our fault, because the head of press has said that to MSNBC. He pointed out the planet hasn't been destroyed yet. Another physicist, by way of reassurance, said that. It's quite hard to destroy Earth. Probably laugh at me, I said that in the Radio Times. I think I've got to finish them. Just let me say that these are real papers, which I think are quite nice just to finish with. One thing you can see is the presence of things called gravitons. Right? So we look for particles called gravitons in the LHC. These are the force carriers of gravity. In many of these models, they're very heavy, and in many of these models, you can see them in LHC. And you can only do that if extra dimensions were present in the universe. So we look for gravitons. This is one of the most highly cited papers about gravitons, and I love the title, which Invasion of Giant Gravitons from Interstellar Space. There was this one, how Bob Locke contained the giant graviton from town in space. And that's what I talked about with these sheets wandering around. So really, I have to finish there because I'm running out of time, but I think what I hope to get across is that LHC has got several layers that it's exploring in the universe, many of which are relevant to astronomy. One which we've done now is the Quark-Gluon Plasma, that we have new data now and we're fighting to understand that and working to understand it. The second one, which is very likely will be solved at LHC, is the Higgs mechanism true, or is there something else that gives mass to everything in the universe? That question will be answered. The nature of dark matter, if you ask many physicists at CERN to guess, they would think that will be answered in the next 2 or 3 years if the machine runs beautifully. And then you have the big question of all, which is the question of the weakness of gravity, which is called often the hierarchy problem, which can be easily phrased as why is gravity so much weaker than the other forces. If extra dimensions are the answer to that, then it may be, and this is on the speculative side, that we see the signatures of extra dimensions as well. So it is probably the most exciting time to be a physicist or a particle physicist in the last several decades, because LHC is working absolutely beautifully. Thank you very much.